Let us begin with the one puzzle that this entire topic is built around. A tiny current at the base somehow controls a current that is hundreds of times larger at the collector. Small current commanding big current. That single idea is what a transistor really is, and it is the reason amplifiers, logic gates, and almost all modern electronics exist. So everything I am about to explain is building toward making that one sentence feel completely obvious. Keep that puzzle in mind because we are going to solve it piece by piece. To get there, we first need one idea locked firmly in place, the p-n junction. A junction is simply the boundary where p-type silicon, which is full of holes, meets n-type silicon, which is full of electrons. Right at that boundary, a thin region forms that has no free carriers in it. We call it the depletion region, and it behaves like a barrier. Now let us bias that junction. Forward bias pushes the p side positive. The barrier shrinks, and at around 0.7 volts in silicon, the junction begins to conduct. Reverse bias does the opposite. The barrier widens and current is blocked. So think of it in the simplest possible way. A forward bias junction is an open door. A reverse bias junction is a locked one. Now hold on to one phrase, because it will matter later. Minority carriers. In p-type material, electrons are the minority. In n-type material, holes are the minority. There are not very many of them. But inside a transistor, they do all of the real work. Keep that idea in mind. There's a common misconception here worth clearing up right away. Many students assume the base to emitter voltage is always 0.7 volts. It is not. That drop only appears when the junction is actually forward biased and conducting. And here is a small exam clue that follows from this. If a problem tells you the base to emitter voltage is 0.7, then that junction is conducting, which means the transistor is either active or saturated and never in cutoff. So if you remember one thing about the junction itself, remember this. Forward conducts at 0.7 and reverse blocks. The bigger idea to carry forward is simple. A junction is a one-way valve, and the direction you bias it decides everything that comes next. Now that the junction is clear, let us actually build the transistor. Take two of those junctions, place them back to back, and have them share one middle layer. That sandwich is a bipolar junction transistor. In an NPN device, you have a heavily doped N-type emitter, then a thin and lightly doped P-type base, and then a moderately doped, physically larger N-type collector. The two junctions inside it are the base to emitter junction and the base to collector junction. The doping is deliberately lopsided. And there is a reason. The emitter is built to flood carriers in. The thin base lets them pass straight through. And together, the two create gain. Here is a misconception worth killing right at the start. People often think you could build a transistor out of two ordinary diodes wired back to back. You cannot. Two separate diodes have thick bases, and the effect I am about to describe simply will not happen in them. The shared, ultra-thin base is the whole trick. That single fact is worth holding on to. Let me give you two quick ways to remember the structure. For the three terminals, think of it like this. The emitter emits, the collector collects, and the base balances. And for the symbol of an MPN, you can remember it as not pointing in because the emitter arrow points outward. So here's the section in one line. A transistor is two junctions sharing one deliberately thin base, and that thinness is not an accident. With the structure in place, we can finally answer how it actually works. This is the heart of the whole device, so stay with me here. Start by forward biasing the base to emitter junction. The heavily doped emitter injects a flood of electrons into the thin base. And here is the key step. Because the base is so thin, almost none of those electrons recombine inside it. Before they get the chance, they reach the base to collector junction, which we are deliberately keeping reverse biased. Now think about what those electrons are. The base is p-type. So inside it, those injected electrons are minority carriers. And this is the important part. A reverse bias junction sweeps minority carriers across with no resistance at all. The very same electric field that blocks the majority carriers acts for these electrons, like a downhill slope that carries them straight into the collector. So follow the whole flow. The emitter supplies the carriers. The collector harvests almost all of them, and only the tiny fraction that recombines in the base has to be replaced through the base terminal. And that small replacement current is the base current. Small base current, large collector current, all coming from one single mechanism. This is where many students get confused, so let us be clear about two things this tells us. First, the base does not power the collector. The emitter does. Second, a reverse bias collector junction is not sitting there doing nothing. It is actively collecting. If you remember only one sentence from this section, remember this. A thin base means the carriers survive, and that is the transistor. Now let us count those 3 currents, because their relationship is one you will use constantly. The idea behind it is just conservation. Whatever current flows into the device must also flow out of it. Put into a formula, that becomes this. The emitter current equals the base current plus the collector current, and that relationship is true always, in every region with no exceptions. The base simply skims a small slice off the main flow that runs from emitter to collector. For a concrete feel, suppose the base current is 20 microamps and the collector current is 2 milliamps. Then the emitter current is 2.02 milliamps. Here is the exam habit to build. If a problem hands you any 2 of those 3 currents, write that relationship down instantly. It is free marks and it is the starting point for most biasing problems. So lock it in as one short phrase. The 3 currents always add up. Emitter equals base plus collector. Now we arrive at the centerpiece of the whole topic, the regions of operation. Here's the core idea. A transistor behaves completely differently depending on how each of its 2 junctions is biased. You have 2 junctions and each one can be either forward or reverse. That gives 4 possible combinations, and so there are 4 regions. Let us walk through them one at a time. The first region is cutoff. Both junctions are reverse biased. There is no injection, so there is essentially no collector current. The transistor behaves like an open switch. A very small leakage current still flows, so it is nearly off, but not perfectly zero. The second region is the active region. The base to emitter junction is forward biased and the base to collector junction is reverse biased. This is exactly the mechanism we just described. It is controlled amplification, and this is the region you use to build amplifiers. The third region is saturation. Now both junctions are forward biased. The transistor is fully on, like a closed switch, with only a small voltage left across it, roughly 0.2 volts from collector to emitter. And here is something important that happens. Once the collector junction also goes forward, it begins injecting carriers back into the base. The base current climbs, and that clean relationship, collector current equals beta times base current, falls apart. The fourth region is reverse active. The base to emitter junction is reverse, and the base to collector junction is forward. This is the device run backward. And because of that lopsided doping we talked about, it performs poorly, and it is almost never used. So let us pause and protect the picture, because 4 regions is a lot to hold at once. Cutoff, both junctions reverse, off. Active, base emitter forward, and base collector reverse. The amplifier. Saturation, both junctions forward, fully on. And reverse active. The backward one we ignore. Now, the single biggest misconception in this entire topic lives right here, so listen carefully. Students hear the word saturation and they think it means maximum performance. In a transistor, saturation simply means both junctions are forward biased and the device is fully switched on. The collector current is now limited by the external circuit, not by the transistor itself. And once more, in saturation, the formula collector current equals beta times base current is no longer valid. Keep that one close because it is the most common trap on exams. One more important note before we move on. Everything I have described so far is for an NPN transistor. For a PNP transistor, you simply reverse every voltage polarity and every current direction. The 4 regions and the entire method for solving them stay exactly the same. So here is how to keep all of this straight in your head. Cutoff is an open switch. Saturation is a closed switch. And active is the analog throttle in between. And for the key numbers, the base to emitter voltage when it is on is 0.7. And the collector to emitter voltage when it is saturated is 0.2. And this leads to the most valuable exam habit of all. When you see any transistor problem, the very first thing your brain should do is ask which region the transistor is in, because every formula you are allowed to use depends on that one answer. So the takeaway for this section is short. The bias of the 2 junctions sets the region, and the region tells you which equations are legal. Now let us go deeper into the active region specifically, because that is where the gain actually lives. Start with this idea. In the active region, almost all of the carriers from the emitter make it to the collector. So the ratio of collector current to emitter current is very close to 1. We give that ratio a name. It is called alpha. Stated as a formula, alpha equals the collector current divided by the emitter current. Its value is typically around 0.99. So alpha is always a little less than 1 and never more than 1. Now here is the more useful quantity. Instead of comparing collector to emitter, we compare collector current to base current. That ratio is the current gain, and we call it beta. As a formula, beta equals the collector current divided by the base current, and its typical value is around 100. On a data sheet, you will often see beta written as HFE. It is the same quantity. And notice what beta really is. It is that opening puzzle. Small current commands big current. Finally expressed as a number, because the collector current equals beta times the base current. These two gains are not independent. They are tied together by a simple relationship. Alpha equals beta divided by the quantity beta plus 1. And going the other way, beta equals alpha divided by the quantity 1 minus alpha. The intuition is easy. Because beta is large, alpha ends up sitting just barely below 1. Let me make all of that concrete with one example. Suppose the base current is 20 microamps and beta is 100. Then the collector current is 2 milliamps. The emitter current is 2.02 milliamps. And alpha is 2 divided by 2.02, which is about 0.99. Notice how every number lines up cleanly. Now, two mistakes to avoid, and these are common. The first mistake is swapping alpha and beta. Remember, alpha is just under 1, while beta is large. They are completely different in size, and they are not interchangeable. The second mistake is the big one for exams. The formula collector current equals beta times base current only holds in the active region. Use it in saturation, and your answer will simply be wrong. So let us reinforce the whole section in one breath. Beta is big, around 100. Alpha is nearly 1. And that beta formula lives only in the active region. So before you ever write it down on an exam, your first instinct should be to confirm that the transistor is genuinely active. With alpha and beta in hand, let us see how all four regions show up together on a single graph. This graph is called the output characteristics. Now, you cannot see it right now, so let me describe its shape in words, and it will make complete sense. On this graph, we plot the collector current against the collector to emitter voltage, and we do that for several fixed values of base current. The shape that results has three distinct zones, and each zone is one of our regions. Imagine the curve. Right near the origin, where the voltage is small, the current shoots up almost vertically. That steep wall is the saturation region. Then the curve bends over into a long, nearly flat plateau, where the collector current stays roughly constant even as the voltage keeps rising. That flat plateau is the active region. And finally, along the very bottom, where the current is essentially zero, that flat floor is cut off. So just from the shape, you can read the device. Steep wall is saturation. Flat plateau is active. Floor is cut off. That is a retrieval cue worth memorizing. Now, to find where your actual circuit is operating on that graph, you draw something called the load line. The meaning behind it is intuitive. Whatever voltage the supply does not drop across the collector resistor is the voltage that is left across the transistor. Put into a formula from the Kirchhoff voltage law. The collector to emitter voltage equals the supply voltage minus the collector current times the collector resistor. The load line is just a straight line, and you only need 2 points to draw it. Here is the first point. When the collector current is 0, the voltage equals the full supply. And here is the second point. When the voltage is 0, the current equals the supply voltage divided by the collector resistor. Connect those 2 points and you have your load line. Now for the payoff. Wherever that load line crosses the curve for your actual base current, that crossing point is the operating point. We call it the Q point, and its position immediately tells you which region you are in. So here is the exam shortcut that strong students use. If a problem gives you the output curves and a load line, go straight for that intersection, because that one point tells you the region and it gives you the current and the voltage all at once. So the key idea for this section is this. One graph plus one load line locates the operating point and names its region. There is one subtle refinement to add about that active plateau. It looks perfectly flat, but it is not quite. If you could zoom in, you would see it slopes very gently upward. The reason for that slope is called the early effect. Here is the mechanism in plain terms. As the collector to emitter voltage rises, the reverse bias collector junction widens its depletion region, and widening that region makes the base effectively even thinner than before. A thinner base means slightly fewer recombinations, which means slightly more collector current. So the line tilts gently upward instead of staying perfectly flat. There is a nice consequence of this. If you extend all of those sloped active lines backward, they meet at one single negative voltage on the axis. That voltage is the negative of what we call the early voltage. And from it, you get a finite output resistance, which is roughly the early voltage divided by the collector current. So here is the exam retrieval cue. If a question ever asks why the collector current is not perfectly independent of the voltage, the two words your brain should jump to are the early effect. And keep this in mind, because that same output resistance is exactly what you will reuse later when you study small signal amplifiers. So the takeaway is short. Rising voltage thins the base and lifts the current slightly, and that is the early effect. Now let us put everything together by working through one complete example, because this is the single most important exam skill in the entire topic. And here is the golden rule before we even start. We never assume a region. We always test it. So imagine a simple circuit. It is a fixed bias NPN transistor. The supply voltage is 10 volts. There is a resistor of 100 kilo ohms feeding the base, a resistor of 2 kilo ohms at the collector, and the transistor beta is 100. Let us solve it step by step. We begin at the base loop. The base current is the supply voltage minus the base to emitter voltage, all divided by the base resistor. So that is 10 minus 0.7 divided by 100 kilo ohms, which comes out to about 93 microamps. Now we make our assumption. Let us assume the transistor is active and use the formula collector current equals beta times base current. So that is 100 times 93 microamps, which gives 9.3 milliamps. And now comes the crucial test. We check the collector loop. The collector to emitter voltage equals the supply voltage minus the collector current times the collector resistor. So that is 10 minus 9.3 milliamps times 2 kilo ohms. That is 10 minus 18.6, which gives minus 8.6 volts. Now pause and think about what that means. A negative collector to emitter voltage is physically impossible. So our assumption was simply wrong. The transistor is not active after all. It is in saturation. So we throw away the beta formula completely and we recompute the collector current straight from the external circuit, with the voltage now pinned at the saturation value of about 0.2 volts. So the collector current is the supply minus that 0.2 divided by the 2 kilo ohm resistor, which gives 4.9 milliamps. Let us confirm that we are right. Look at the ratio of collector current to base current here. It is 4.9 milliamps divided by 93 microamps, which is about 53. That is well below beta, which was 100. This ratio has a name. It is called the forced beta. And whenever the forced beta is less than the real beta, that is the formal signature of saturation. It confirms that the circuit is limiting the current, not the transistor. So here is the classic exam mistake to avoid. Many students stop at 9.3 milliamps and report it as the answer. The verify step is exactly what separates a correct answer from a wrong one. So commit the whole routine to memory as a simple sequence. Assume active. Solve. Check the collector to emitter voltage. And if it comes out impossible, you are in saturation. So let us pull this entire topic together into one clear picture. A transistor is two junctions that share one thin base. Through injection and collection, it lets a small current control a much larger one. The emitter current always equals the base current plus the collector current, no matter what. And the bias of those two junctions sets the region. When both junctions are reverse, you are in cutoff, an open switch. When the base emitter is forward and the base collector is reverse, you are in active, the amplifier, where the collector current equals beta times the base current. When both junctions are forward, you are in saturation, a closed switch. And the fourth region, reverse active, we simply ignore. And remember, for a PNP transistor, you just flip every polarity and nothing else about the method changes. Now burn the key numbers into memory. The base to emitter voltage is about 0.7 volts when it is conducting. The collector to emitter saturation voltage is about 0.2 volts. Beta is roughly 100, and alpha is just below 1. And hold on to the four big traps. A transistor is not just two loose diodes. The beta formula only holds in the active region. Saturation means fully on, not maximum. And you must always verify the region before you trust your answer. Get all that down, and you will be able to solve the standard exam problems with confidence. More than that, you will walk into amplifier circuits and switching circuits already understanding what is happening underneath them. And if you take away only one single idea from everything we have covered, let it be this one. Always identify the region first. Because once you know the region, everything else simply follows.